So we're going to play Peg Solitaire. Do you remember the rules? Okay, we have many squares forming this cross and pegs all around the squares, except for the center one. The allowed movements: we can take a peg, jump over another, it gets removed, landing on an empty square. Rewinding. Yes. Okay, we can do the same from left to right and in columns, going up or going down until there's only one left. But we'll change the board. Let's use an infinity board this time. You can put the pegs anywhere below the red line, and you have to reach the squares above the red line, leaving only one peg. Can you do it with squares on the first row? Oh, that's easy. Just one movement and we're there. Okay, another one, a little more difficult. The second row above the red line. Let's use the same pegs we used before, and with two more, well, we can reach it. No, another one. Let's try to reach the third row. Seems interesting this time. Let's start with everything we put before and some more pegs, and with some movements we can do it. But wait, what does this has to do with mathematics? Bear with me just a moment, we're getting there. As a challenge, you can try to reach the fourth row, but don't try to reach the fifth row. It's impossible, and that's exactly what we're going to demonstrate here. Okay, that's the point of the video. We're going to use energy, a concept from physics. Let's put energies on the squares. Each square has its energy, starting with 1 on the target square, and we multiply by alpha going down the central column. Going left or right, we take this column and multiply by alpha again, so that every column has energy in geometric progressions. The energy at any time is going to be the sum of energies of every square which has a peg on it. What the possible movements are, what they do with the energy. Well, if we have pegs on alpha to 5 or 4 and go to 3, or 9 and 8 go to 7, we have this changing energy in general. If you do the reverse, we just change the signs. The energy of pegs going closer or going away the target square. We can also jump the central column, and the change of energy is this expression. We haven't talked about alpha yet. Let's put a value on alpha so that the energy when the peg gets closer to the target square is 0. It does not change. We have to solve this equation. I'm pretty sure I've seen this before. Oh, golden ratio, what a surprise. Actually, it's inverse. Using this value as alpha, the energy is conserved when we jump approaching the target square. When going away or crossing the central column, the energy decreases. It never increases, it only decreases. Okay. What would be the energy if every square below the red line is filled with a peg? Infinitely many pegs. Well, let's sum the infinite geometric progression of the central column and the adjacent ones, and the adjacent of the adjacent, and so on. Let's remember the formula for the sum of the geometric progression. Initial term divided by 1 minus alpha. Yes, we do it for every geometric progression. We can factor 1 minus alpha in the denominator, and we get another geometric progression. We can do it again, the same formula. Just this time, let's put everybody under the same denominator. And this is the expression for the total energy. Okay, let's calculate it, but no need to take into account the value of alpha. Another surprise, we can do it only using the equation it satisfies. Remember, this one. So we can say 1 minus alpha is alpha squared. Okay. So we can substitute the denominator. We get alpha to the 4th power, and simplifying again, we have exactly 1. You know what that means? With infinitely many pegs, we have energy equal to the square we want to reach. With less than that, and we'll never be able to reach that square. Wow, amazing. So that's it. Try to show this demonstration to somebody close to you and put in the comments what was the reaction. Thanks for watching.